Hello, in this lecture I will discuss the formation and evolution of a low mass star in a binary system. First, we must understand what exactly a low mass star is, and that is a star which has less than two solar masses. The solar mass is the mass contained within the sun. The sun is the metric for which the solar mass is used. The point is that the sun is used as reference or a constant for which to look at everything else. This is a molecular cloud, also known as an interstellar medium. These are low density and low temperature clouds of dust and gas that exist within space, which can reach up to 1,000 light years across. These clouds have a mass which can range from 1,000 solar masses to 3 million solar masses. Within these clouds are regions called clumps, which have higher densities but still low temperature. And within the clumps, there are even denser and colder regions called cores. These are the embryos of stars. When a star is first forming, the conditions within the core, which are low temperature and hence low pressure and high density and hence greater gravitational attraction, both work together to give gravity the advantage, which brings all the material together. Eventually, the gravitational force of the infalling gases becomes strong enough to overwhelm the pressure exerted by the cold material that forms the dense cores. The material then undergoes a rapid collapse, and the density of the core increases greatly as a result. The natural turbulence inside a clump creates a spinning motion. According to the law of conservation of angular momentum, a rotating body spins more rapidly as it decreases in size. This is what happens when a core contracts to form an object called a protostar. As it shrinks, its rate of spin increases. A protostar is an object which is created by a dense core that is contracting to become a true star, but has not begun the fusion of hydrogen protons to produce helium. The third stage in a star's evolution is fusion. As the gas cloud collapses due to gravitational forces, the core becomes hotter and its density increases. Eventually, the temperature and density reach a pinnacle where a process called nuclear fusion occurs. Fusion is the action of combining lighter atoms to form heavier atoms. In order for a star to be on the main sequence of the HR diagram, it must fuse hydrogen into helium. Two hydrogen atoms must collide to fuse into a helium atom. Fusion is what creates the internal pressure within a star's core for stability. The star must fuse hydrogen first because hydrogen is the lightest element. Stars are classified on the Hertzsprung-Russell diagram, also known as the HR diagram, and they're classified by their temperature in kelvins and luminosity in terms of the sun. The main sequence is a line in the HR diagram where 90% of all stars lie. So in the picture in the bottom right, that's this area here. 90% of all stars lie on the main sequence at any given moment because 90% of stars spend their lives fusing hydrogen. A star's life is defined as the amount of time it's fusing atoms. A star does not remain on the main sequence solely because it's fusing hydrogen, but because of the attributes that a star maintains while it is fusing hydrogen. Stars fusing hydrogen at particular masses are different temperatures and have different luminosities which correlate. Once the fusing of hydrogen ceases, the relationships between luminosity and heat change. It is the 10% of stars observed that are no longer fusing hydrogen, which make up the stars no longer on the main sequence. These stars are also experiencing the last 10% of their life. Upon the depletion of hydrogen in the core contains helium. The helium in the core can be thought of as the accumulated ash from the nuclear burning of hydrogen during the main sequence stage. Energy can no longer be generated by hydrogen fusion, and the fusion of helium requires much higher temperatures. Since the central temperature is not yet high enough to fuse helium, there is no nuclear energy to supply heat to the central region of the star. The period of stability now ends, gravity takes over, and the core begins to contract. Heat generated from the contraction flows outward to where it is a bit cooler. In the process, the heat raises the temperature of a layer of hydrogen that has spent the whole time just outside the core where it was not hot enough to fuse. The compression of the core due to gravity has now provided the area where this hydrogen has been lingering with fusion-enabling temperatures. New energy produced by the fusion of this hydrogen now pours outward from this shell and begins to heat up layers of the star farther out, causing them to expand. Most stars generate more energy each second when they're fusing hydrogen in the shell surrounding the helium core than they did when the hydrogen fusion was confined to the central part of the star. Thus, they increase in luminosity. The expansion of the star's outer layer causes the temperature at the surface to decrease. As it cools, the star's overall color becomes red. This is why the star in this stage is known as a red giant. In comparison to the main sequence, a red giant will reside in the upper right of the diagram due to its low surface temperature and high luminosity. Once a core is compressed enough, the heat within the core reaches temperatures of 100 million Kelvin. Once this temperature is reached, the fusion of helium can begin. In order to fuse helium, it requires that 3 helium atoms collide. This process produces carbon atoms. When carbon atoms collide with helium atoms, they produce oxygen. So the new core will now consist of carbon with a smaller percentage of oxygen. The process of helium fusion is similar to hydrogen fusion. The star becomes smaller and stabilizes, although it does not return to the main sequence. Upon the depletion of helium atoms to fuse, the core collapses once more, and the heavier compressing core is now reaching even hotter temperatures and reaching even further out into the atmosphere. The heat from the compressing core reaches a layer of helium and a new layer of hydrogen, which was not reached previously. And this causes the star to swell back up again. This stage is where low and high mass stars diverge. The carbon-oxygen core requires a greater amount of compression than a lower star is able to compress to. With the lack of fusion, the star has now died. This stage in the star's evolution is called white dwarf. Gravity is in complete control due to the lack of internal pressure. Gravity compresses the core to a point where a law of nature must prevent further compression. This law is the Pauli exclusion principle. It entails that 2 electrons cannot be in the same place at the same time doing the same thing. The place of an electron is its position in space. What it is doing is its motion and the way it's spinning. In order for a white dwarf to be compressed anymore, an electron must violate this law of nature. Hence, the white dwarf is as dense as physically possible. An Indian-American astrophysicist named, pardon if I butcher his name, Subrahmanyan Chandrasekhar was able to calculate how much a star will shrink before the electrons halt its further contraction, and hence its final diameter. When Chandrasekhar made his calculations about white dwarfs, he found that the radius of a white dwarf shrinks as the mass in the star increases. A white dwarf with a mass of about 1.4 solar masses or larger would have a radius of 0. What the calculations mean is that even the force of electrons cannot stop the collapse of a star with more mass than this. The maximum mass that a star can end its life with and still become a white dwarf is 1.4 solar masses, and is called the Chandrasekhar limit. So let's say that in a binary system, one star has become a white dwarf, and the other star is gradually transferring material onto it. As a fresh layer of hydrogen from the outer layers of its companion accumulates on the surface of the hot white dwarf, it begins to build up a layer of hydrogen. As more and more hydrogen accumulates and heats up on the surface of the star, the new layer eventually reaches a temperature that causes fusion to begin in a sudden and explosive way. The white dwarf quickly and briefly becomes quite bright, hundreds of thousands of times its previous luminosity. This is called a nova. If a white dwarf accumulates matter from a companion star at a much faster rate, it can be pushed over the Chandrasekhar limit. When its mass approaches the Chandrasekhar limit, it begins to contract, and as it does so, it heats up, and new nuclear reactions begin in the core. This simmering phase ends in less than a second, when an enormous amount of fusion takes place all at once, resulting in an explosion. The fusion energy produced during the final explosion is so great that it completely destroys the white dwarf. Afterward, no trace of the white dwarf remains. This has been the evolution of a low mass star in a binary system.